We're in Chapter 1. Chapter 1 is all about problem solving. So in Section 1.1, we're going to look at problem solving with inductive and deductive reasoning. So first thing we have to cover is what in the world are these? So the type of reasoning that forms a conclusion based on an examination of a specific example is inductive reasoning. So here we go from an example to a pattern. Okay, so this is an example to patterns. Okay, or as some people would tell you, specific to general. Okay, is inductive reasoning. So the conclusion formed by inductive reasoning is often called a conjecture. C-O-N-G-E-C-T-U-R-E, conjecture. And it's called a conjecture because we don't necessarily know if it's correct. We're just basing it off of the information that we have. So if you examine a list of numbers and then predict the next list according to some pattern that you observe, you are using the inductive reasoning. Okay, so we're going to go ahead and look at two examples. So the first example that we have here is 3, 6, 9, 12, 15. So looking at this, every time from here to here I add 3. And then we add 3 again. And then we add 3 again. So that means the next piece, we would assume it continues, and we would add 3, and we would get 18. The next pattern that we see is 1, 3, 6, 10, 15. Now this pattern isn't quite as straightforward as the last one we did. So to get from 1 to 3, we add 2. To get from 3 to 6, we add 3. To get from 6 to 10, we add 4. To get from 10 to 15, we add 5. So what do you think is going to happen next? Well, because these are going up by 1, then what's going to happen next is we're going to most likely go up by 6, which means the next term would be 21. Okay, so again, these are two different types of patterns. This one, everything was the same, but this one, there was a pattern, like another pattern inside the differences. So it's just going to vary on what type of pattern that we're using. Now, a statement that is a true statement is provided it's true in all cases. Okay? But sometimes you can find just one case in which a statement is not true, and this is called a counterexample. And that makes the whole statement a false statement. So we're going to look at 3 examples of this next. So first example, we have the absolute value of x is greater than 9. So what this means is that whatever number we put in here, we have to take the absolute value of it. Absolute value means the distance from 0. And then we have to prove it's greater than 9. So we're going to look for some we want to find at least 2 counterexamples, and then some values that also make it true for each of these pieces. So let's try 10. So if we say x is 10, then we get the absolute value of 10 is greater than 9. Well, the absolute value of 10 is 10. 10 is greater than 9. That's true, because the answer is yes. Let's try another one. Let's say the absolute value of x is negative 11. So we take the absolute value of negative 11. Is that greater than 9? That's what we're testing. So the absolute value of 11 would be 11, because we're 11 away from 0. Is 11 greater than 9? Yes, so those statements would work. Now let's pick something that would make it false. So you could say, 0. You could say 9. So I just want to show you that 9 would be false. So we're going to plug it in just like before and evaluate. So the absolute value of 9 would give us 9. And then we're testing, is that greater than 9? And you might want to say true here because they're the same, but we can't, because 9 is not greater than 9. They are equal. which means that this would be a false statement. So that means that x equals 9. This would be a counterexample. This is one counterexample. Now let's find another counterexample. So let's try x equals -8. So the absolute value of -8, is that greater than 9? Well, the absolute value of -8 would just be 8. Is 8 greater than 9? No, 8's less than 9. So then this would be another counterexample. So let's try another one. So here we have x squared equals x. So now we're going to take x squared equals x. So we're going to try some numbers just like we did over here. So let's try x equals 0. Make it easy on ourselves. Try 0 first. So we get 0 squared. Is it equal to 0? Well, 0 squared is 0. It's equal to 0. That's true. So we got 1. That's equal. Let's try 1. X equals 1. Then we get 1 squared. We're checking if that's equal to 1. Well, 1 squared is 1. So 1 equals 1. That's true. Okay. Now, if this is really a true statement, it's true for any number that we can plug in. So it can also be true for -5. So let's try -5. So -5 squared, is it equal to -5? Well, when we square a negative, it becomes positive. And when we square 5, we get 25. So is 25 equal to -5? The answer is no. So then this would be a counterexample. It doesn't just have to be a negative number. This is also false for positive numbers. So like if we tried x equals 2, 2 squared, is it equal to 2? Well, 2 squared gives us 4, because we get 2 times 2. 4 is not equal to 2, so then this would also be a counterexample. So we got our 2 counterexamples. So next we're going to try another one involving squares. So for this next one, we are trying to figure out some values that work and don't work in the quantity x plus 1 squared. The quantity squared, so we're going to add then square, or if we square then add, x squared plus 1. So here we're really kind of testing order of operations just to show you that they're different values. So let's start easy just like we did before. Let's test 0. X equals 0. So we get 0 plus 1 squared. Is it equal to 0 squared plus 1? Well, 0 plus 1 gives us 1. 1 squared is 1. So on this side, on the left-hand side, we get a 1. Now on the right-hand side, 1 squared plus 0 squared plus 1. 0 squared first gives us 0. Add 1, we get 1. They are equal, so this is true for x equals 0. But let's try another number. Maybe there's a number that doesn't work. So let's try something else. Let's try x equals -2. Because again, if this is really a true statement, it's going to be true for all numbers. All numbers. Okay? 2. X equals -2. So we get parentheses -2 plus 1. We're going to square that. Is it really equal to -2 squared plus 1? -2 plus 1 is in parentheses. We do that first. We get -1. Square it. Over here, -2 squared gives us 4. Then we add 1, so on this side we get a 5, and this side we get a 1. Those are definitely not equal, so this would be one of our counterexamples. Okay. Now everything we're doing so far is kind of nice, round numbers, no decimals, no fractions. These are called integers. Okay. But we don't have to be limited to integers when we're working with these. We can use fractions. We can use decimals. So let's try it. Let's try this one with a decimal instead, or a fraction. So I'm going to do x equals a half. This would be the same results if you use x equals 0.5. So you can go either way. I like fractions better because I think they're a little easier to work with, especially if we're going to be squaring things. So we're going to go half plus 1 squared. Is that equals to half squared plus 1? So this would give us 3 over 2. Then we square it, so we get 9 over 4, which would be 2.25 if you're doing this, because you can absolutely do these on a calculator. There's nothing that says you have to do them by hand. I just prefer to do it by hand. 1 over 2 squared would give us 1 over 4. We add 1, so now we have 5 over 4. So just looking at this, we can already tell that the 9 over 4 is definitely not going to be the same as 5 over 4. 5 over 4 is 1.25 if you're a decimal person, so either way, this is a false statement, so it would be a counterexample. So again, counterexamples don't have to be integers. They can be decimals and fractions as well, and they don't have to be positive. They can be positive or negative. So this is where you can kind of get creative by picking your favorite number and then seeing if it works. But if something is false, odds are there's more than one number you can plug in to find that counterexample. There's more than one number. So there's all kinds of numbers that you can try. But again, this is just to kind of show you that even though it's true for some numbers, it's not always going to be true for all numbers. Now, if you do a couple of these and you're kind of testing if something's true, like if you're solving an equation, if it is true, if something is true, it's going to be true for, again, all numbers, just like we said up here, it's going to be true for all numbers. So all of these would be true if it's really an equivalent expression.